Have you ever wondered how your smart speaker knows it's you talking in a crowded room? Or how a robot could just turn and face you when you call its name? Well, it's not magic. It's this fascinating technology that gives machines a kind of superhuman hearing, and we're about to break down exactly how it works.
So how can a device pinpoint a sound in three-dimensional space? That's the big question, right? The answer is surprisingly elegant, and believe me, it has huge implications for the future of tech.
We're really talking about a technology that goes way beyond what our own ears can do. It's about giving our devices a whole new sense, the ability to not just hear sound, but to understand its exact location in the world with incredible precision.
Now, the technical term for this whole thing is sound source localization, and it's a fundamental challenge in acoustic signal processing. Cracking this problem, well, it opens up a whole new world of possibilities for the devices we use every day.
Okay, so how do they actually do it? The core principle is based on something our own brains do intuitively all the time. But of course, machines can do it with a level of precision that is truly superhuman.
It all comes down to this one concept: time difference of arrival, or just TDOA for short. A sound wave will almost always hit one microphone a tiny fraction of a second before it hits another. And that tiny, tiny delay is absolutely packed with information about where the sound came from.
The whole process is actually pretty simple in concept. A sound is made, the wave expands, and it hits one microphone just a moment before the other. The system's entire job is to measure that tiny delay with incredible accuracy. We're talking down to the microsecond. By comparing these delays across multiple microphones, it can start to build a 3D map of the sound's location.
So what's the best setup? Well, you can get a basic direction with 2 or 3 mics, but the ideal arrangement for true 3D localization uses 4 microphones, and they're put in a tetrahedral shape. Think of a pyramid. This specific geometry gives you the best possible spatial coverage to pinpoint a sound anywhere in 3D space with the least amount of hardware. Pretty efficient.
But of course, it's not that simple. I mean, if it were, this tech would be everywhere by now. The real world is, well, it's messy, it's noisy, and it's full of echoes. And all of that presents a huge challenge for our simple TDOA principle.
In a lab, you can get a nice, clean signal. But in the real world, that very same signal is competing with traffic, other people talking, and reflections bouncing off every single surface before it even reaches the microphones. So the challenge isn't just hearing the sound, it's isolating it from all that other junk.
And these are the main culprits. You've got constant background noise, echoes or reverberation, and something called multipath effects, which is just the sound bouncing all over the place. Add to that the need to do all this in real time and keep the hardware perfectly synchronized, and you've got yourself a seriously tough engineering problem.
So, how do engineers solve it? The solution lies in this brilliant combination of tiny, powerful hardware and some incredibly clever software algorithms that are designed specifically to just cut right through all that noise.
Here's the toolkit that makes it all happen. The hardware has these tiny, high-quality MEMS microphones and a powerful but low-cost ESP32 chip that does all the heavy lifting. But the real magic, the secret sauce, is in the software. An algorithm called GCC-PHAT to find the signal in the noise and a Kalman filter to track sounds that are on the move.
The GCC-PHAT algorithm is like the system's first line of defense against chaos. It's so clever because it mostly ignores how loud a sound or its echo is. Instead, it focuses purely on the timing, the precise moment the wave arrives. This is what allows it to effectively tune out all those confusing echoes and just lock onto the original direct signal. It's genius.
And once the system has a lock, the Kalman filter takes over for any sounds that are moving. Think of it like a prediction engine. It's constantly predicting where the sound will be next, and then it uses the new microphone data to correct that prediction. This creates a super smooth, continuous track instead of a jerky, inaccurate one.
So, does it work in real time? You bet it does. The average processing time, from the sound first hitting the mics to a 3D location being calculated, is just 67 milliseconds. That's faster than a blink of an eye. And crucially, it's fast enough for interactive applications like robotics and virtual reality.
And how accurate is it? Well, this system didn't just meet its design goals, it completely smashed them. It achieved an azimuth, that's side-to-side, accuracy of 2.8 degrees, and an elevation, or up and down, accuracy of 1.9 degrees. That is incredibly precise, and it proves that you can get high-end performance from low-cost parts.
This brings us to the most exciting part.
Now that we have this powerful, accurate, and affordable technology, what can we actually do with it? What does it mean for our world when our technology develops a real sense of hearing?
The applications are just vast and so exciting. I mean, imagine robots that turn to face you when you speak, security cameras that instantly point towards the sound of breaking glass, truly immersive VR where the audio perfectly matches the visual world, or even advanced hearing aids that can isolate one single speaker in a noisy room. The possibilities are really transformative.
And that really gets to the heart of this project. By proving that this level of performance is possible with cheap, off-the-shelf parts, this work helps democratize the technology. It takes spatial hearing out of expensive labs and puts it into the hands of developers and creators everywhere.
Which leaves us with this one final thought. We are on the cusp of building a world where our technology is constantly listening, not just for our commands, but to understand the environment around it in a completely new way. So the only real question is, what will it hear?